for my presentation is my topic for my presentation is topological NIR, topological near infrared spectroscopy. So what is topological NIR spectroscopy? It could be pronounced top NIR for short, and top NIR is still NIR, but uses what is a topological method to interpret the data. It is a model that takes NIR data and then converts it into different clusters of data points, and by creating these little pockets of clusters, it is able to predict the physical and chemical properties of other samples by looking at its neighbors. From what I found, this is typically used for petroleum products, anywhere from crude to stream products, all the way to gasoline and diesel. This technique was first used in a refinery back in 1992. And how it works is that a model is constructed from a calibration set with measured multivariate responses and corresponding known sample concentrations or the physical characteristics of interest that we are looking for. Once the model is made and you got all your data points, the model is then cross-validated with a validation subset that is different from the calibration subset. So once you calibrate it, you then you have your data points for your calibration, then you have your data points for to validate that, hey, you are within range of what you're going for. So how we go about doing that is there's a process called densification. So a model goes through densification where it improves the robustness of the model. What the model does is you take at least 30 samples, usually from the plant. So if you're going from a specific refinery, you'll take like 30 samples from that specific location of where you're working at, and then you use hundreds of other reference samples, and you include that in your library. And so by increasing the number of samples in your library, this top NIR model can make predictions across the whole of the operating envelope and can deal with, inliners and outliers. So like any data point that you can put into the model just helps it. And when you it can even take in mistakes and basically just makes it where it can predict a wider range and give a more general range of the predicted properties instead of trying to narrow in so quickly. So the instrumentation used for this method, you can use any NIR. What I found was, most companies just sell NIR, so you just need NIR to first run your sample, and then from there you have to use the top NIR software, and that's usually sold by your vendors. Different vendors have their own different versions of this software, but they each do the same thing. They each take, they build a library and they create little envelopes of clusters that look at specific characteristics of that sample that you're looking for, and then cross-references it to other nearby neighbors to predict your unknown. So NIR instruments, from my job, we tried buying an NIR once, and from what I remember, the one we were looking at cost a little over 60 grand. And so obviously you can have more instruments that can be more expensive. So anywhere from 60 to up, as I say, is the general range for the instrument. And now that's just the instrument itself, but what we're looking for is the top NIR, and that's a software, and that usually costs extra. So you buy the instrument, and then you got to buy the software that, can interpret your data that's given off from your instrument. And so that's extra. The analysis time to run, from what I found, top NIR, it's less than a minute. Other NIR instruments run anywhere 3 to 5 minutes, but what I found, finding this, it's usually they take about a minute. Your resolution and your sensitivity depends on how many data points are in the model. So if you want more resolution, you need more data points. The model predictions are accurate as long as the unknown is sufficiently similar to your calibration set. And then inaccurately predicted samples can be put in to revise the model, as I said earlier, to have more generality. So more about the instrument, since it is NIR, the energy source is a laser. The laser passes through a 1 centimeter cuvette, and it does involve the vibrational transition of the molecule. From what I found, the top NIR is looking at the 4,000 to 5,000 nanometer range, and it is used for petroleum products and anywhere from crude, as I said earlier, to finished products. And since we're looking at petroleum, most of our products are going to be liquid samples, and they're usually put in a cuvette. Some of the data outputs I have here on my screen. The first slide is a typical NIR graph, from the 4,000 to 4,800 range. The next, the graph on the right is a picture of a model like before densification happens, and then on the bottom left is a graph of densification, after that has happened, so you can see everything's more clustered. And then the bottom right is typically what a picture of the top NIR would look like. So as you can see, there's like a little circle of envelope, and it's got some data points, and your unknown is your X. So basically, you make all these little envelopes of what properties you're looking for, and so whatever property this is, you have other samples with that same property at different values, and then your X, it goes and looks at its neighbors, and it's able to predict, well, I know this point is this point is that, so, and my unknown is here, so it must be close. And that's how that works. And then on the next slide, I have another view of another top NIR. How would that look like? And I said, so basically, you find your unknown, and it gets put into this envelope, into this little cluster, and then basically, it just looks at everything around your point, and finds this little cluster, and from whatever, what your reference and calibration samples were, it knows what those are, and then it can predict yours based on what it knows of everything else. So, as I said, the technique of the top NIR, it relies on a larger database of samples for representation. It has an extensive library without the need to add a lot of samples to the database from the lab or site or facility that you're bringing the samples from. The process of this densification allows it to be tailored uniquely to the production site. It is robust and can be extended to meet new process conditions. The model allows to be updated without manual recalibration. It has reduced model maintenance and downtime, and then with a new product or feedstock, the model looks for the closest spectral neighbor. So it can be a completely unknown. You got a new product coming in feedstock, and you put it on this model, and it can predict because it'll find what it looks closest to. It'll look at the other neighbors of the data points, and it'll be able to predict. And so it can cope with multiple process stream operating envelopes. So like you can look at different properties at the same time. And then some other benefits going on, it's a non-linear database. So you're not making, a calibration curve or anything. You're not making a straight line. You're making little envelopes and clusters, and you're just comparing to where it falls in the group. So it's very accurate, and it's very fast. I said, it only takes a minute to run, and it can provide multi-property predictions with a wider prediction range. And like I said, you can include outliers, but most of the time you won't, but you can, and you'll have more generality of your prediction. Some disadvantages is that if your little operating envelope ever changes, the spectra will change, and so the search for your neighbors will gradually fail as the operating point leaves the original envelope. So you'll start moving out of that little envelope of your properties that you're looking at. And it is difficult to get both accurate and robustness within the same model. So if you want accuracy, you got to take out the outliers, but if you want more robustness, you keep the outliers and you start losing some accuracy. So another problem is it does not highlight outliers in a direct way. And so all types of mistakes, from operator to typos, just too bad samples are enlarged in modeling during the densification process, and that does leave with a larger standard error prediction that is present and reports if mistakes are in the densified sample population. So some applications for this, I said earlier, it's mainly used for petroleum physical properties. Some of those physical properties include a RON and MON, which is your octane numbers, your RVP, which is your read vapor pressure, density, distillation, so all your different cut points, 5, 10, initial, 90%, your vapor over liquid ratio, your cloud point, your flash point, freeze point, cetane number, cold filter plug-in point, your PIONA, which stands for paraffins, isoparaffins, olefins, naphthenes, and aromatics, your benzene percentage, MTBE percentage, toluene percentage, xylene percentage, and then just some little additional info. This technique can be used in tandem with another technique called PLS, which is partially square. So basically, it's a process of running your NIR, quantifying your data, run this technique, and then run this technique, or run this technique and then that, and then you just get more accurate results. And then I have a little picture of a model, where you start. So you examine the data, you process it, you make some estimations, you validate it, you predict some more, you validate the prediction, and you just kind of go in a circle until you're complete. And that is my presentation. Thank you, and I appreciate your time.